remembering to record this time. And I will stop the timer before the alarm goes off. All right, hello, welcome back. We are boldly forging ahead. I know that this stuff is coming really fast and there's just no way to avoid that. I strongly encourage you to try and keep up. One of the ways that I am, structuring the course in order to encourage you to keep up is by doing a chapter's worth of material, then kind of sending you to go do that homework. Knowing that the next time we meet, I'll be able to go over any questions you have from the homework, and that after those questions, we have a quiz on it right then. So it's just, encourages you to keep up and not fall behind. And I know that falling behind is a terrible thing, especially in a really short 6-week kind of course. I used to really be concerned about scheduling an exam on the calendar flip. So like I wouldn't want to schedule an exam on August 1st because you're kind of going through your life and then you flip the calendar and say, oh no, I have an exam. But I don't think many people use a regular monthly wall calendar anymore anyways. So August 3rd is exam number 1. That means today we're going to be doing chapter 14, and then we'll have a quiz on chapter 14 on Tuesday, next Tuesday. Next Tuesday, we'll cover chapter 15. And once we've covered chapter 15, we have covered all the material that will be on exam number 1. And you would have had a quiz on each chapter along the way. So you see some of the questions that I asked on this kind of material. And then on Thursday, whatever the date is, next Thursday, we'll go over any questions you have from the practice exam. There's a practice exam on our Canvas page. To help you prepare for the exam. It's actually 2 practice exams because I used to divide up chapters 11 and 12 into one exam and 13, 14, and 15 into a second exam, but it's all one exam for us. So there's practice exam questions to give you practice doing these problems so that nothing surprises you on exam day. So next Thursday, 1 week from today, I'll go over any questions you have from the practice exam, then specifically going over any questions you have from the chapter 15 homework before I give you a quiz on chapter 15. And then the next time we meet, so a week from today is Thursday, the following Tuesday will be exam number 1 on chapters 11 through 15. That's all we're going to accomplish that day. So when we do that, I'll have time to answer questions if you have them. I know from teaching experience that on exam day, sometimes people just come to class and are like, don't talk to me, don't say anything, don't go over any problems, just give me the exam. And you'll have the ability to just launch into the exam if you want to. But if you have questions, I can answer them ahead of time. And then I will be here with you on Zoom to answer questions that come up while you're taking the exam. So that takes us through that date. And then we pick up with chapter 18, 19, 20, 21, 22. After that. It seems like a pretty short turnaround. The time we've had up through exam 1 and then the time we have through exam 2. Exam 2 material is not quite as expansive as exam 1 material is. and we're in the groove now where we can keep making progress and moving forward. So, there's the plan. Okay, let me share. So just to review, on our Canvas page, I will post the recording from today a little bit later. Today we're going to do chapter 14, and then I will field any questions you have from the chapter 13 homework before I encourage you to start the chapter 13 quiz, and I will be here with you on Zoom chat while you're taking that quiz. The whole course is here on Canvas. You can look ahead to chapter 15 if you want to. And then when you click on next week, you will find the practice exam. I also do a walk through the practice exam key. I do encourage you to try the practice exam before you go looking at the key. It is super easy to convince yourself that you understand something that maybe you don't if you're looking at the answer. So it's important to look at the question as though you were trying to answer it on an exam, come up with a strategy, look at the equation sheet, see how you would start to put things together. Go ahead and put them together and run the numbers, see if you get the right answer. And then if you didn't, you can look at the key, or even if you did, to find out if you had the right answer, you look at the key and kind of confirm with yourself how you did there. So, do be familiar, Salem State has academic integrity regulations, and I am doing a lot of this with the honors system. I know some of my colleagues have done all sorts of challenging pieces where they do a lockdown browser, and there's like maybe you're paying for a subscription service to somebody who's going to be proctoring the exam, and they're watching where your eyes are looking while you're taking the exam, and that just seems unwieldy, at least to me, and it just kind of sets a tone that I don't want to set. I want you to give me your best effort, and if you don't do great the first time through, you have a second chance, open book, open note, to keep your average score. So hopefully I'm making the stakes not so high that you feel like cheating is worthwhile. I don't want you to cheat. I want you to do your very best, and then we can work with that. I can check in with you if you're struggling, and we can hopefully make things make more sense. So that's my thinking. Okay, chapter 14. At some point when I made this PowerPoint, I think I had gotten behind in lecture. And so this PowerPoint is going to review some of the stuff we talked about last time. So I'm going to go quickly through those slides. I think it's maybe helpful to kind of hit those points one more time in context before we move on to the methods of heat transfer, which really and truly are pretty straightforward, the heat transfer methods. So, I think it's okay to have this in context, that what we've been talking about is this idea that the kinetic theory of gases, that you can have a bunch of particles, atoms, molecules of a gas trapped inside a container, and those molecules are bouncing around, hitting the walls, hitting each other, doing all sorts of things. But because on average they are spaced very far apart, we're able to treat this as a gas, not as a liquid. And we can make some assumptions about a range of velocities and a range of directions of motion and all sorts of things that give us access to this world of statistical thermodynamics, which sounds horrible, and it kind of is, but we're gonna get to the point, the punchline of these equations, which includes that there's this distribution of molecular speeds at any given temperature, which shouldn't be terribly shocking to anyone if you've been in a chemistry lab and you have a couple of reagents that you heat up to a certain temperature. The reaction doesn't just go bang all at once. When you heat something up to a certain temperature, some of those molecules are at a very high speed and some are at a relatively low speed. And in terms of speed, in terms of energy in a collision, maybe that energy is at the activation energy for a chemical reaction to proceed. So that's kind of the idea, is that there's a simplified version of things that we've been presented with in life, and then there's kind of a more realistic range of possibilities at any given what we call temperature. So 300 Kelvin is just, it's right around room temperature. 1200 Kelvin is really hot. And for anything, there's a range, a distribution of molecular speeds. So as we considered gas molecules moving inside a container, we first had something going in one-dimensional space. It's just bopping back and forth in the x-axis. And then we recognized that realistically there are 3 dimensions. So when we have 3 dimensions, we're going to divide by the number 3, and we have volume in the length of the box cubed. And we come up with this equation for the pressure, force over area, the pressure that the gas molecules are exerting on the walls of the container. And it's the number of particles divided by 3, 3-dimensional space, mv squared over L cubed, the volume. So we come up with, ultimately, takes a little bit of moving the variables around on either side of an equation. But if we take volume and multiply it by both sides of the equation, we get pressure times volume. PV, well, ideal gas law says PV equals NKT, the number of particles, Boltzmann's constant, and temperature in Kelvin. So when we do that substitution, then we can cancel out N, and we can rearrange the stuff in here to pull out what we would like to have is an expression that has 1/2 mv squared, because that's kinetic energy. And so when we do the math in there to pull out a 1/2, we get this new equation that says kinetic energy equals 3/2 kT. So that is an equation that falls out of following the kinetic theory of gases that can be really useful to us for certain applications. It's saying that the energy carried by atoms or molecules in the gas phase inside a container is the only thing that matters is the temperature, which is consistent with the laws of thermodynamics that we're building up from square one, which includes that at 0 Kelvin, at 0 temperature, there is no kinetic energy, there is no motion. So we have an argument for this equation, which may be a little simplified, but works for an ideal gas, and it's useful to us. Likewise, because kinetic energy is 1/2 mv squared, we multiply both sides of the equation by 2, then we get 3 kT divided by mass equals v squared. And so v, the actual velocity of average velocity, root mean squared velocity of a molecule is going to be the square root of 3 times k is a constant, temperature in Kelvin, divided by mass. I haven't graded all of the quizzes, but be careful when you're doing something under the square root, that you do the top line altogether, the bottom line altogether, and then take the square root of everything. There's just so many, you can set everything up so that it looks correct on a piece of paper, but if you put it in incorrectly in your calculator, you get the wrong answer, and I feel sad. And that's your goal in this course, to not have me feel sad. So there's the speed of nitrogen atoms at 20 degrees Celsius, 293 K. And then we built up, using that same bit of information, the internal energy or potential energy of a monatomic ideal gas at a given temperature is 3/2 capital N kT, the number of particles, or 3/2 lowercase n for the number of moles, times R times temperature. In Kelvin, always in Kelvin. Talked about phase equilibrium and evaporation a little bit. That at that distribution of molecular speeds at a given temperature, some of the molecules are highly energetic and will jump out of the liquid phase into the gas phase. And eventually, if it's a sealed container, there will be an equilibrium reached, which we call vapor pressure. And that is enough of that. Okay, now to truly chapter 14 material, talking about the transfer of heat. Convection, conduction, and radiation are the 3 mechanisms of heat transfer, which we'll kind of flesh out a little bit right now. So, convection is the bulk flow, bulk movement of a fluid. So when you put a pot on the stove to try to boil some water, what happens is that the molecules of water that are in closest contact with the heating element will get warm. Warm things are a little less dense. Less dense things tend to rise up. More dense things, what the cool water up near the surface, will sink down. And so you get this mixing of the fluid inside there until it's all evenly heated up to its boiling point, and then it starts to boil. When my wife and I first moved to Salem, Massachusetts, we bought a unit in a condominium on Lafayette Street. And in that unit in our condominium, the heat that we had was ceiling electric heat. I had never seen that before. I have never seen that since. It is the dumbest thing in the world. If you ever, I don't know where you are right now, but if you have heating elements where you are, typically it's something that would be called baseboard heating. You would see something near the floor. Maybe it's baseboard electric, maybe it's baseboard forced hot water, I don't know what, but it's something that is low on the floor. Why? Because the air molecules that are near that heating element will get warm, and then heat rises. Those air molecules will rise up. The colder air molecules near the ceiling will fall down, and you will get even heating in your room. In our condo unit on Lafayette Street with ceiling electric heat, we turned on the heat and there were heating elements in the ceiling that warmed up the ceiling. And there it stayed. So you would be sitting down in the room feeling kind of chilly. And then if you stood up, maybe the top of your head would feel a little bit of the warmth. My wife spent a little time in Africa in college and actually contracted malaria. And she said it was very reminiscent of her experience with malaria. Her feet were cold and her head was hot, and it wasn't pleasant. So we wound up getting space heaters. Maybe a ceiling fan would have worked well in that place. I don't know, but it was just a really silly way of heating. But that's the idea of convection. It's this bulk flow of molecules. So you use that in heating your house. A hot water baseboard heating unit will warm up the air molecules. Heat rises, which really just means that the density of the air molecules that are warmed up are less dense. Therefore, they rise up compared to the more dense air molecules around them, which sink down, and you get this convection heating. My little family at some point decided we're not going to fight physics anymore. And growing up, the freezer part of our refrigerator was on top and the refrigerator part on the bottom, but that doesn't really go with convection. What you would want is the coldest part of your fridge, the freezer, to be on the bottom, and then the, obviously you want it to be a little bit warmer where you're keeping your eggs and milk. You don't want those frozen on top, but that happens with a refrigerator as well, this convection. Weather patterns are often influenced by places that heat up and cool down. A glider could, travel on a flow of air that is rising up from the warm ground up into the upper atmosphere, which is generally a little bit cooler. What happens here is that the sun shines down on the earth and air is largely, air doesn't absorb sunlight. What does absorb sunlight is dark ground or dark pavement. So the air on the ground gets warm and then the warm air rises up. The cool air comes back down. Automobiles, everything has some sort of forced convection where you're trying to keep your engine from overheating by moving coolant fluid throughout. All right, there is convection for you. Another method of heat transfer, remember that we can have high temperature regions and cold temperature regions, and heat will naturally flow. And I kind of gave away the punchline there, from the region of high temperature to a region of low temperature. trying to achieve some sort of thermal equilibrium. So conduction is the process where heat flows directly through a material. If you've ever, I don't know, try to make analogies with my life experience. If you've ever roasted marshmallows over an open fire, you generally get a stick and maybe put the marshmallow on the end of the stick and hold it into the fire. On occasion, I've had metal skewers from like making, you know, some other food. And if you put a metal skewer with the marshmallow in the end, hold it into the fire, metal is a really good conductor of electricity, but also of heat. And so it gets warm on the end. Metal things tend to distribute the heat throughout the thing. It conducts heat easily through the material. So some things are good thermal conductors. None of my kids played football, but all of my kids played in the marching band. And you go to a stadium where they play American football or, you know, marching band event, and there's generally aluminum seats in the stand. And for whatever reason, the season that this is happening is always wicked cold. November, Thanksgiving, you know, maybe into December sometimes. And you sit down on the metal seat in the stadium and you feel very cold. Why? Because it is conducting heat away from your body. Unless you're a smart person and you bring a blanket or a cushion to sit on the aluminum seats, in which case there's an insulator there. So things that conduct heat well are called thermal conductors. And if you have any experience with electricity to this point, you might be aware that there's good electrical conductors. Wires, metal wires are good electrical conductors. They're also good thermal conductors. And then there's some things that aren't good at conducting heat. And those would be insulators. And things that are good thermal insulators tend to also be good electrical insulators. So there's that. We have an equation this time. We didn't have any equations with convection. So if I ask you questions about convection, you might be expecting more conceptual kind of questions, maybe, you know, write something or a multiple choice question like that. But with conduction and radiation, we actually have some equations. Those are just more convenient for me to ask you a question because I can provide the equation on a data sheet and you just have to demonstrate that you know how to use this equation to get to the answer. So here we have two regions of different temperatures separated by some length, distance, and the x-axis. And the material that we're talking about has a cross-sectional area here labeled A. If it was a circular thing, or it's another word I'm looking for, it will come to me later, area would be pi r squared. So there's that. So here's what has been found experimentally. The heat that flows, heat is Q, remember, in joules. Heat that flows through a rod, that was a metal rod in our previous diagram. Heat that flows through the rod will increase the greater the area of the rod is. That makes sense if it's a tiny little wire versus a big, you know, circular metal thing. The bigger pathway that the heat has to transfer through, the more heat will be transferred. It also increases proportionally to the temperature difference from one end to the other. So when we talk about heat being conducted through a material, temperature matters. Your home, If you want to keep the inside of your house at like 70 degrees and it's 60 degrees outside, there won't be a ton of heat going out of your house and into the world. But if you keep your house at 70 degrees and it's 0 degrees outside, then a lot more heat, any places that aren't well insulated, will conduct a lot more heat out into the world outside. Heat flow is time dependent. It takes time for heat to flow through a material. And so it increases with time the longer that it's colder out and there's a pathway, a mechanism for heat transfer, the more heat transfer will happen. And then the heat that flows will decrease with the length of the rod. So again, this idea that the length of this thing, the shorter it is, the less, the shorter the conducting material is, the less heat will pass. So this is just another image to try to put this through. I guess this is rectangular, so area is just base times height, but time, temperature difference, cross-sectional area, and the length of this conducting material. So here is the equation. Again, I will offer my apologies on behalf of physics. On this exam, we will use the letter lowercase k to stand for Boltzmann's constant. And you will need to know that one in context, as opposed to this version of lowercase k in this equation, where k is going to stand for the thermal conductivity constant for a given material. Typically, if I give you a question that involves this equation, I will say, you know, you're using, I don't know, a piece of iron, and for iron, K equals something. I will give you a number for K so that you know to use that number and don't get it confused with Boltzmann's constant in that case. So this is the equation that is built off of these assumptions that we just made, that, you know, it's bigger with area, it's bigger with the change in time, it increases linear, or bigger with the change in temperature, it increases linearly with time, and then inversely proportional to the length of the thing. And so we have Q equals Ka delta T, change in temperature. It never hurts to convert to Kelvin, but anytime that we have delta T, you could use Celsius or Kelvin. It doesn't matter because the degree size is the same. Time and then the length that it has to pass through. Now, very, very often, we will, sorry, divide both sides of the equation by time, and we'll say Q over time equals Ka delta T over L. And the reason we would do this, Q over T is joules per second, which is watts of power. So if you want to know how much power it takes to maintain a certain temperature, or if you want to know how much heat in watts is lost through a window or a door or whatever we're talking about, we would often do this thing where we divide both sides of the equation by time to get joules per second. Joules per second is power. Right. So again, I will likely give you the thermal conductivity constant for whatever material we're talking about. You will note that the aluminum stadium seating in the high school football stadium has a very high thermal conductivity constant. And you will notice that things like air have a very low thermal conductivity constant. So they're not a good conductor, they're a good insulator. So when you're going outside in the cold, the advice is to dress in layers. Sometimes you have a big puffy coat. The puffiness of the coat is something that is trapping layers of air around your body such that it's a good insulator. And then other things are good conductors. You don't want to be going around in the cold in a good conductor. And if you're, I don't know, it's summertime now, if you're, you know, exercising, you want something that will actually conduct heat away from your body very well. So not that you want to dress in metal, but there's other materials that can serve as a good conductor. In many dwellings, there is insulation. Insulation is sometimes that fiberglass pink fuzzy stuff, which is again trapping pockets of air for insulation. Sometimes it's kind of that hard, you know, it's kind of squishy, but it's like a styrofoam board thing that you use for insulating. And inside that is little pockets, and those little pockets are trapped air. That air is a very bad thermal conductor, which makes it a good insulator. They're inside the pockets of air, there may be some convection currents, but since it can't go anywhere, it doesn't really do anything. So there's just a good insulator. Here's the same equation again, because I took a couple of different PowerPoints and put them together into one thing. Asbestos is a good insulator, but turns out it also does bad things to your lungs and gives you cancer. So they don't use that one so much. All right. I'm not going to go through the whole calculation here, but this is a typical kind of question that you might see with the information that we have so far. So what is the rate of heat loss? So the rate is what we've been saying. Rate is Q over T, joules per second, equals K A delta T over L. So K for glass, wood, or air are things we would look up. Glass 0.84. Watts per meter Kelvin. It should be a capital K. The units for a constant like this is just collecting all the other units in the equation. So it's nothing to get too concerned about. So for each material, we put in the thermal conductivity constant, and then the area, 1 meter squared, and then the temperature difference. Delta T is the change in temperature. So outside it's 0, 0 minus 21 is negative 21 degrees C or Kelvin, it doesn't matter. So if it was Kelvin, then it would cancel out there, and the one of the meters would cancel out. And then in the denominator, the trick here, it said 0.5 centimeters. We need to have the units matched. So we need to convert centimeters to meters. The quick way to do that is 0.5 times 10 to the negative second meters. That's what centi stands for. times 10 to the negative second. And so everything cancels out except for watts, which is joules per second. And so you run the numbers and you come up with a rate of heat loss. It would be a negative number because the heat is traveling through the 0.5 centimeter thick window made of glass, or I don't know why you would make a window out of air, but maybe you'd have shutters or something to be wood. Anyways. And then, you know, in practical sense, there's a benefit to having layers of materials. So you could figure out what's going to happen if you have insulation with one property and then wood with another property, and figure out what the amount of heat conducted through the wall in 1 hour. The trick there is you come up with joules per second, and then you figure out how many seconds are in 1 hour and do that. Okay. Walking you through. Okay. So here in Salem, Massachusetts, and other places that are right by an ocean, you will find that it tends to have a cool sea breeze during the day. Why? Because the sun is shining down on the surface where it can be best absorbed, which is the land, the green grass, or the pavement, or even, you know, just sand, has a little bit darker, able to absorb solar radiation better than the sea, which is largely reflective. And so the hot air molecules move up, the cool air molecules that are surrounding it will move in to fill their place, and you feel a cool sea breeze during the day. And then at night, the primary mechanism of heat loss is through infrared. That's how heat moves. And so infrared light will leave the land and go up into space. And then there's certain gases that absorb infrared radiation effectively. And that can be like carbon dioxide. And so if there's too much carbon dioxide in the air, that absorbs a lot of the infrared radiation and heats up, and you get this thing called global warming. All right. So the other thing, and this, again, I'm sorry, this seems really difficult, but it's foundational to everything we've been talking about, that everything radiates heat. Everything that's at a temperature higher than absolute zero is emitting heat. And it likewise can also absorb solar radiation or other forms of radiation, absorb energy in the form of radiation. So all objects give off electromagnetic waves, infrared, visible light, ultraviolet light, etc. You turn on the burner on your electric stove, you'll see it glow. You can actually see it emitting radiation. So the amount of energy radiated by an object due to its temperature is proportional to its surface area and also to the fourth power of its temperature. So that's the temperature squared and squared again to the fourth power of its temperature. But it all depends on emissivity, which is a number between 0 and 1 that indicates how effectively something radiates or absorbs radiation. So things that reflect tend not to absorb or emit radiation very much, and things that absorb all the radiation do tend to. So the classic example is a white car parked in the sun in a parking lot and a black car parked in the sun in a parking lot. If you've ever had that experience, the white car tends to reflect a lot of the solar radiation. And so if you touch it, it doesn't feel as hot. It doesn't absorb as much heat and it doesn't emit as much heat. The black car, black body radiation is the classic term for this thing that we're seeing here, Planck's black body radiation. Something that doesn't reflect will absorb, and so the black car is not reflecting a lot of the sunlight, it's absorbing it, and if you touch it, you will feel very hot. So maybe don't go touching other people's cars in parking lots, but if you happen to see a friend with a white car or a black car, go ahead and get that sense. So here's the equation. Again, this is power, this is watts, joules per second. E here, epsilon, is the number between 0 and 1, the emissivity of the object. And typically we'll make it be 0 or 1. I guess 0 will be pointless. We'll make it be 1. Sigma is a constant. It's the Stefan Boltzmann's constant. It's a different Boltzmann's constant than the one we're using for gas law. 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the 4th power. Area is just area. We'd have to give you something to work with there. And then temperature in Kelvin to the 4th power. So here it is all again. And so I guess you could do it in terms of the solar radiation coming from stars or the stellar radiation. So 2900 K to the 4th power is going to be a huge number, such that it's emitting 4 times 10 to the 30 watts. And then I guess in this example, we're going to figure out the radius of the star, and it's enormous. Try not to go too crazy with radiation questions because the numbers are pretty enormous, and those are an added challenge the way we do things on Canvas. Okay, if you've ever seen or used a thermos bottles are one of those things that are designed with everything we've talked about in mind. A thermos bottle will have a stopper with a gasket, all made out of non-conducting materials, generally plastic or rubber, which will keep heat from leaving your hot coffee inside your thermos by way of convection, right? Because the air molecules can't rise up and leave through the top. You have a cover on top to keep heat loss minimized by convection. If you take the cap off of a thermos bottle and look inside, you see that it's a silvered, a reflective surface kind of mirrored in there. That is to deal with the radiative heat loss. All of the heat is reflected back into itself so your coffee doesn't get cold. And then if you've ever had the experience, it's typically either a vacuum seal or just some sort of layer of insulation to minimize heat loss by conducting straight through the material. I mentioned that air is a good insulator. An even better insulator is vacuum. So heat doesn't travel through a vacuum. So the vacuum of space, heat isn't traveling from one place to another. Radiation is. The radiation energy that the Earth absorbs, we get in the form of heat. The only way for the Earth to cool down, to lose that heat, is by radiation. That's infrared radiation is how the Earth will shed extra heat. And if we have greenhouse gases that absorb that infrared radiation, then all that heat gets trapped here in our atmosphere, and that can be problematic. All right, and then I have other things that we've already talked about. So I don't know that we need calorimetry yet. Oh. I think we have time to, oh, I should look at this. Hold on one second. I need to make sure that I'm covering everything for the chapter 14 homework, or else I will have failed you today. Methods of heat transfer, heat required, heat transfer, condensation, heat transfer. Yeah, we're good. We're good for chapter 14. Okay. We have more work ahead of us with chapter 15. That will be coming. Okay, so chapter 14 homework, you are, I believe, equipped to tackle this now. I'm back to more sensible videos of me just working on a chalkboard instead of some other things that I've tried. So that's good. Okay. It is time to change gears and start thinking about the quiz on chapter 13 material. The quiz is largely based on the chapter 13 homework. And so I am delighted at this time to answer any questions you have. And some questions are coming in on chat, and I'm keeping an eye on those, and I will hopefully answer those to your satisfaction before I encourage you to take the quiz. Conceptual questions, nobody ever really asks conceptual questions. So just to kind of point out, two systems are in thermal equilibrium when they're at the same temperature. That's what thermal equilibrium signifies. Heat is transferred from a higher temperature object to a lower temperature object until the two objects have the same temperature, and then we say they're in thermal equilibrium. One method of getting a tight fit, say of a metal peg in a hole of a metal block, is to manufacture the peg slightly larger than the hole. The peg is then exerted when at a different temperature than the block. Should the block be hotter or colder than the peg during insertion? So you probably would figure out that you want the block to be hot such that the size of the hole expands. You put the peg in, it's got a nice tight seal. So the room temperature or cold peg goes in, and then you let the block cool down to room temperature, and suddenly you have a very good seal. Just trying to impress you with the size of a mole. That's hardly conceptual, it's kind of mathematical. So whatever, okay. So I see a question on number 28. calculate the number of moles in the 2-liter volume of air in the lungs of an average person, air being at 37 degrees Celsius. So the number of moles is just a number, right? So you can revert back to chemistry gas constant. You can use the gas constant that you would typically use in chemistry class with the liters atmospheres per Kelvin mole. Since they gave us liters here, or you can convert liters to cubic meters and use the value that we've been using. It's truly, one thing that I find a little annoying is when there's multiple ways to the same right answer. But I think in real life, you should be flexible with that. There can be multiple paths to the same right answer. So pressure, we're going to assume that this person isn't going to explode and die. So normal atmospheric pressure. So if we did liters atmospheres per Kelvin mole, then we would do 1 atmosphere times a volume of 2 liters divided by R, 0.082 liters atmospheres per Kelvin mole. And then temperature 37 degrees Celsius plus 273.15 to convert to Kelvin. So 37 plus 273.15 is 310 Kelvin, 310 K. So the number of moles is denominator 0.082 times 310. And then I want to do 1 over that number times 2 liters. And I get 0.0786 moles. Some of you will get questions on today's quiz incorrect because you fail to convert from degrees Celsius into Kelvin. Please don't let that be you. I feel bad when people forget to do that. Yeah, I just don't want that to be you. So number 50, there's a table. Is this even a table from our textbook, which goes through some of this information. I don't think I have a vapor pressure question on this quiz because I decided that that was kind of cumbersome for the context. Let me check that so I'm not misleading you. Today's quiz is not short, but I don't think I get into vapor pressure. Preview. Yeah, there are no vapor pressure question, so I'm not gonna get into that. So your numbers on the quiz are different than these numbers. They change every time. All the data that you need is here. I guess I was a little bit coy, and I just pointed out that Boltzmann's constant is R divided by Avogadro's number. So 8.31 divided by 6.022 times 10 to the 23rd. So that's 1.38 times 10 to the negative 23rd. So let me equals 1.38 times 10 to the negative 23rd joules per Kelvin. So when you use Boltzmann's constant, there it is for you. All the other information, I think, is here. Let me double check. Yeah, I give you the alpha value for steel for the Eiffel Tower. So, well, come on, get this back to where it was. Okay, so if there are no further questions, I will encourage you to go ahead and tackle the quiz. I am here on Zoom chat if you need me. I'm going to stop recording and I will post the